Nearly 500,000 lines of Anthropic's internal codebase were recently exposed through an accidental mapping file in an NPM registry. While the industry immediately looked for model weights or algorithmic secrets, the true value of this leak is the orchestration layer, the specialized environment that surrounds the model. This orchestration layer acts as an agentic operating system. In this architecture, the large language model serves as a central processing unit, while 4 distinct subsystems manage the actual work. These subsystems are designed to handle the core hurdles of autonomous coding: state persistence, process isolation, context compaction, and concurrent tool execution. These 4 pillars are engineered to bridge the gap between a probabilistic text predictor and a deterministic agent capable of managing a complex software repository. Looking at this code suggests a specific engineering philosophy, that the capability of a frontier AI assistant depends more on the design of this rigid structural harness than on the raw reasoning of the model itself. Standard LLM APIs are inherently stateless. Every time a developer starts a new interaction, the model begins with a total lack of memory, requiring a complete contextual reset before it can generate useful output. Anthropic addresses this amnesia in the memory and state subsystem. The harness forces a continuous execution loop, where a 40,000-character configuration file, known as Claude.md, is injected into the context at the start of every single turn. This file establishes the specific coding standards, architectural guidelines, and repository patterns the agent must follow. By continuously loading these instructions, the harness creates a pre-computation environment that biases the model towards the specific engineering taste of the user's team. Without this, resuming an existing project would require a massive token tax, the computational waste of cold starting a new agent session from scratch. To maintain continuity, the harness uses a secondary state mechanism, persistent output capture. Every interaction is saved into JSON-L files bound to unique cryptographic session IDs. This logging allows a developer to fork and resume specific sessions exactly where the execution paused, maintaining the system's focus. This aggressive level of state persistence transforms an isolated text prediction into a continuous, uninterrupted project workflow. Parallel execution is the primary goal for any agentic system, but it often fails when multiple agents try to modify the same files on a single branch, resulting in destructive merge conflicts. The leaked code reveals 3 distinct sub-agent execution models designed to prevent these collisions: fork, teammate, and get worktree. Within the process execution block, the get worktree model appears as the primary solution for safe parallel processing. This architecture isolates individual sub-agents into entirely separate physical branches on the disk. Because they are physically separated, agents can write, test, and break code simultaneously without ever colliding with the user's main working branch or with each other. This model is efficient because all isolated worktrees draw from a single centralized prompt cache. The system shares the read source while keeping the write destination separated. Sharing the prompt cache eliminates computational redundancy, allowing the system to spin up 10 or more sub-agents without multiplying the cost of input processing. Parallelism requires strict process isolation at the system level. Simply adding more agent threads is ineffective unless their execution environments are explicitly walled off. There is a common industry assumption that feeding massive codebases into 1 million token context windows results in better software generation. In reality, context bloat causes generative fidelity to drop significantly once a window accumulates more than 200,000 tokens of noise. The memory management block reveals a 5-layer compaction architecture designed to systematically destroy unnecessary data to keep the context clean. Layer 1 is microcompact, which clears old, irrelevant tool results based on how much time has passed. Layer 2, context collapse, reduces the token footprint by summarizing standard conversational spans. Layer 3, session memory, extracts key workflow states and technical learnings to be saved in external storage. Layer 4 is a full compact, forcing a lossy, overarching summarization of the entire operational history. The final failsafe is PTL truncation, which ruthlessly deletes the oldest remaining message groups to stay within the model's limits. The harness also enforces a strict rule for large file outputs. They are written directly to disk, and only an 8 kilobyte preview is ever allowed back into the context window. Effective agentic memory is defined by what the system chooses to forget. By prioritizing token density over data volume, the harness maintains high operational accuracy. With a library of 66 internal tools, the system must be strictly governed to prevent catastrophic errors in the codebase. Within the I/O system, tools are split into two categories. The first are concurrent tools, read-only operations like file scanning or web browsing. Since these tools cannot modify the environment, the harness allows them to execute in massive parallel swarms. The second category are serialized tools. These perform mutating operations, such as direct file edits or bash commands. Forcing these mutations into a single file sequential pipeline eliminates the risk of race conditions, where multiple agents try to write to the same file at once. Because the architecture uses token streaming, a developer can cheaply interrupt and halt the agent if they see a mutating operation beginning to drift, saving computational costs. By partitioning tools based on their potential to alter the system state, the agent can move quickly when reading and methodically when writing. This leak clarifies exactly how frontier coding agents achieve high-level performance. The engineering takeaway is clear. The LLM is a processing unit, but the harness is responsible for managing memory, isolating processes, and governing I/O. These specific mechanics, active layered compaction and get work tree isolation, can now be extracted and applied to open-source projects. Incorporating these structural constraints allows developers to improve the reliability and safety of smaller, local models. The legacy of the Claude Code leak is a verified architectural framework for autonomous development, providing the community with the patterns needed to build the next generation of coding agents.